Okay. All right. So we started talking about first order circuits, right? And DC sources. So DC source, what's it mean to be a DC source? Direct current. And it's constant, right? Okay. AC source, and they're constant with respect to time. So as time advances, it doesn't change. Okay. AC source changes as a function of time. So a sine wave source is pretty common. You'd find those at the wall outlet. You'd find those at the antenna on your phone or something like that. Okay. So what we did is we said, okay, well, the circuits that we're going to deal with, the classic example typically is an RC circuit where I have a resistor and a capacitor. And you guys know that what should happen is when I close that switch, the capacitor is going to charge up. And eventually, if this voltage source over here is a DC voltage source, if that's 5 volts, what's going to happen to the capacitor over time? It's going to go to 5 volts, right? So we said in steady state, what's always true. So steady state is when? What do we define steady state as for these things? Because there's 2 periods of time we consider, right? One is steady state and the other one is transient. Okay. What is steady state? Yeah. So when I get to the point where all the voltages and currents are constant. Okay. And so if I wait long enough, I'll get there. All right. And so in this case, when that capacitor charges up, what's he look like? What kind of, we can replace the capacitor once he's charged up with what kind of circuit element? Open circuit. All right. Once the capacitor is charged up, it's an open. Once an inductor is magnetized, that's the right term, not charged, but once it's magnetized, then we say that the inductor is a short circuit. Okay. Until then, it's a capacitor or an inductor, and we have to analyze the circuit. Now, this guy is a pretty simple circuit. All right. I got one R and one C. Most of the circuits you get are not going to have one R and one C. Now, they're going to have one C because this is what type of circuit? It's first order, right? It's first order, it has one energy storage element. The second order, which will start next week, that's when I've got 2 energy storage elements. All right, and then funky stuff can happen when I have 2 energy storage elements. And we don't ever deal with 3 or more. All right, and there's reasons for that. Basically, anything with 3 or more can be described as something like 1 or 2. Okay, so we don't need to learn 18th order circuits. We learn first order and second order. Okay, all right. So what I did the other day is I basically said I separate this guy into a set of 6 steps. All right, I just want to talk through those 6 steps kind of carefully. So what I'm going to do is 2 examples where I go through these 6 steps. Okay, so the first one, determine the initial value of the capacitor voltage or inductor current at t equals 0 minus. So in any of these problems that we get, 0 minus is basically going to be a steady state condition before the switches move. So I wrote here at this note before steady state. So it's a steady state before we do the transient period. Okay. In that time, we're going to assume the circuit's been in steady state for a while. We're going to look at where the switches are. And we're going to replace the capacitors with opens, replace the inductors with shorts. Okay. Step 2 is to get the final value of the capacitor voltage or inductor current at the end of the whole thing. So after the switches have moved, so it's at the end of the problem. So I called it the after steady state. So the before, meaning before any of the switches move, after, meaning after the switches move. Okay. And then steps 3, 4, and 5 here deal with the transient condition. All right. That's the time when the capacitor is charging or discharging or whatever. Okay. During that time, we're always going to convert the circuit down into a Thevenin or Norton equivalent. Okay. And really, it's going to be a Thevenin equivalent every time. All right. So that's the part probably going to focus a lot of time on over the next couple of lectures is how we do that. Because that making a Thevenin or Norton is not necessarily everybody's strongest point yet. So that's something we got to work on. Right. But what if I have a Thevenin equivalent circuit? What the heck does it look like? What's in a Thevenin equivalent circuit? Series. It's a series circuit. What's in the series? One voltage source and one resistor in series. Okay. Somehow we've converted the whole network into that. It's a really useful idea. Like I said, the other side of that wall outlet, there's an electrical engineer that designed the lighting system in here. that lighting system is connected to the North American power grid. He doesn't analyze the whole North American power grid to figure out what the lighting load is going to be, right? He knows that you can simplify it down to one voltage source and one resistor. Okay. All right. So we're going to go through these 6 steps. And so the example I started doing the other day, we're going to start it from the beginning again. All right. This was the circuit here. And I've got basically those 6 steps defined for myself in basically these parts of the problem. And I don't think I saved it. I did this. I want to figure out not I of t, not v of t, but I of t. Okay. All right. So I want to figure out the current here, and that's not easy for you to see there. It doesn't look great on the screen, but that current has been defined to be going that direction, going down. Okay. All right. So we're going to go through those 6 steps. So part A is my step 1, part B is my step 2, so on and so forth. Okay. So we're going to go through that process. Now, before I do that, the thing I also said I was going to do here is I was going to give this to you as an example. So I created this as an example problem. Now, when you guys go in to submit stuff in MATLAB, this is exactly what it's going to look like to you. All right. It's going to have a bunch of variables that it's solving for. Now, what I'm going to do is I'm going to make MATLAB. This is MATLAB here, what this window is. I'm going to make MATLAB do the math for me. You don't have to. If you sit there and you're like, MATLAB's confusing and it's hard and I don't know anything about it, that's fine. Do this on your calculator and put the number in right here. That'll work. All right. I don't recommend doing that. Right. I would actually script it like I'm going to do here. In other words, I would actually put the math in as I go, but you don't have to if you're not comfortable with that. Okay. But I will continue to do problems like this in MATLAB throughout the semester to get you more comfortable with it. All right, because it is nice to use. Okay. All right. So let's go through the process. So the first thing I want to do is, and what I'm going to do right now, we'll come back to, let's go to full screen so we don't hear my emails chiming and stuff. I'll take a second for it to. Okay. All right. All right. So here's our circuit. And I'm going to skip ahead to the next slide here. So my first step is I want to figure out what's the current at 0 minus. And I said that 0 minus is basically the moment right before the switches do whatever the switches do. And I'm assuming everything's in steady state. All right. So in this case, what's happening at t equal to 0? Switch is opening or closing based on that picture? Switch is opening. All right. Switch is opening. And I'm saying I'm in steady state. So I want to simplify this circuit over. How do I simplify this circuit for that steady state condition? What's that? What's the step that I got to make? Make the inductor a short circuit. Okay. So basically I got my 2K over here. I have a short circuit for this guy. And I'm going to call it IL, and I'm going to call it IL of 0 minus specifically. The 2K is there. The 12 volts is there. And then the 3K, and then the 6 volts. And the 6 volts is turned around. Like that. All right. So that's the setup I got there. And I want to figure out IL of 0 minus. I want to do it the same way I started to do it the other day, which is to say that I want to use superposition. Okay. So if I use superposition, I'm going to say IL of 0 minus has 2 parts. I'm going to say it has I1 and I2. I1, okay, I got, what the heck is superposition again? Why has it got 2 parts? What am I doing?
Turning off one source at a time.
Turning off one source and doing the analysis one at a time, right? So for I1 here, I'm going to say this is for the 12 volt source. 12 volt source on. This guy is going to be with the 6 volt source on. Like that. All right. That's going to be my basic approach. I want to figure out what I1 is first, and then I'm going to figure out what I2 is. All right, so if I want to figure out I1, so I1's with a 12-volt source on, I guess I didn't write it here. That also means with the 6-volt source off. So if I turn a voltage source off, that means that its voltage becomes 0. Okay. If its voltage is 0, what do I do with the voltage source? Short circuit. Okay. So for I1, I would have what? I would have the 2K. I'd have my short circuit for the inductor. I'd have my 2K, my 12 volts. And then over here, I'd have this 3K. And I can move that 3K. I moved it physically where it's sitting in my schematic, but I didn't move it electrically, right? It's still in the same place that it was before. It's not on top anymore, but electrically it's in the same spot, right? I haven't changed anything about where it is. Okay, and I did that on purpose because I like it better that way. All right, now, the other day I said that the 2K and the 3K have no current in them. Why is that? I should be careful about this. This 2K and that 3K have no current in them. Why do I know that? Because there's a short in parallel with them, right? So I'm gonna be careful about this. The reason I know that there's no current through here is because there's a short in parallel. So the way I do that real quick is I'll do a KVL around this loop right here. And I'll say 0 equals I times 2K, where I is the current in that 2K resistor. So what does I have to be? 0. All right. So remember the other day I said KVL, KCL, Ohm's law. That's it. That's all this class is. Okay, that's still true. All right. So I don't remember things like, well, a short and parallel with a resistor means no current. What's everybody say? Current likes the path of least resistance or whatever, right? Yes, it does. But why? Because KVL says so. All right. So the same is true with the 3K, right? Because I could do a loop. In other words, I could do a KVL loop that included this short and this 3K. There better be no current through that guy either. Okay. So what that all simplifies down to is to say that I get this circuit that looks like this. $2K and my 12 volts like that. And I can solve. All right. Now, to solve this guy, I don't need to be too careful. I know that, I mean, I could do KVL and I'd say, here's my plus minus on that resistor like that. And I would see that I1 is equal to what here? What would my I1 be? Well, it'd be, yeah, 12 divided by 2000. Which I don't even really care what that number is. You're right, it does become 6 milliamps, but I'm just gonna say it's 12 divided by 2000. Okay. I'm gonna let MATLAB do the math for me. All right, that gives me I1. I also needed to find I2. What was I2? What was that one? Circuit with the 6 volt on and the 12 volt off. Okay. So the 12 volt is off, it gets replaced with a short circuit again. So that means that for I2, I have 2K short circuit with I2 in it. I have the 2K resistor just by itself, right? And then I have this 3K and this 6 volt source like that. All right, now, real quick, just making sure how much I left for myself here. Okay, so looking at this circuit here, what do I do with the two 2Ks? Do I need to worry about those? No, why not? No voltage across them. That means there's no current through them, right? So they really don't exist for me. So basically that says that this whole circuit simplifies itself down to a short circuit the 3K ohm resistor and the 6-volt source. Now, if I look back at the picture I drew, I2 is going down, right? So I got to make sure I stay that way. So I2 is going down. Now I got to figure out, this is one of those ones that always gets tricky with minus signs and stuff, right? Because my 6-volt source is going in a funky way, right? What I have to do is, for me at least, I don't like to skip steps, all right? I'm going to write a plus minus like that on that resistor, and I'm going to give that a number. I'm going to call it V3, all right? And I like to define for myself that V3 equals, how would I write that? How's that equal in terms of the currents and the resistances that I have there? How would I write that? How would I write V3? In terms of the way I2 is drawn, how would I do that? V3, so V3 equals I2 times something, right? How would I set this up?
3,000.
Was it?
3,000.
3,000 times I2, not negative?
It could be negative in sense, right?
It is, so I2 is going to enter the plus terminal, right? And so given the way I've written this, it's 3,000 times I2, right? So if you follow, so I2 is the current everywhere in that loop, right? So if I2 is entering the plus terminal, I'd write it this way, okay? All right, so I always like to do that real carefully because, you know, the only circuits is easy, right? It's all about making sure you keep the signs right as you go through all those steps. That's all it is, right? That's so everybody gets caught up in the details of it, but you got to be real careful about those steps. So take it slow, all right, and you'll get it right, all right. You'll see as we get to the exam, when I ask you particularly problems like mesh and nodal, if I asked a mesh problem and said, give me the mesh currents, every one of you would be wrong. I know that. If I asked you for a number, every one of you would get it wrong. Because what I'm more concerned about is that you know how to set the problem up right. And I'm going to ask you for the equations. You'll see that in the homework, right? I ask you to set the equations up. I know that you're going to mess up the equations. What I'm most concerned about is that you guys know the basics of being able to set up the equations right, because that's what the whole class kind of comes down to. All right. So take that stuff slowly. I'm trying to emphasize that because that's where you learn this stuff is when you take this stuff slowly. Okay. All right. Enough of that. So I've written this out. Now I got to figure out what I2 is. So what do I do to figure out what I2 is? I'm going to do KVL, right? Now I always do my KVLs in a clockwise direction, right? And I always start at this corner and go around. So I'm going to say 0 equals, and then I go through that resistor from the minus terminal to the plus terminal. So I would say minus V3, right? Given the way I define that. And then I go from the 6-volt from the minus to the plus. So I say minus 6 like that. All right. You guys with me on that? All right. Okay. So basically I end up with V3 equals negative 6. All right. V3 is 3,000 times I2 is equal to negative 6. I2 is equal to negative 6 over 3,000. Okay. Now, that negative sign bothers people sometimes. What's the negative sign mean? It doesn't bother me at all. Don't let it bother you. It just means that it's going the opposite direction of the arrow, right? Which sort of makes sense because, right, if you look at this, current would have to be leaving the plus node of that battery. It would have to be going against that arrow. That's okay. All right, totally okay. It just means it's going a different direction than what I wrote here. Okay. So now I'm done with my first step, right? My first step here was to figure out for myself I of 0 minus. And we said I of 0 minus was going to be equal to whatever I1 is plus whatever I2 is. So we figured out that IL of 0 minus is equal to I1 plus I2, which in this case is 12 over 2,000 minus 6 over 3,000. All right, when we could get a number for that, we will. All right, but for now, that's the key thing is you guys can follow that process. All right, questions about how I got through that first step? All right, let's keep going. All right, so the second step. Now I want to find I of infinity. What's I of infinity? What did I call that? That's a steady state again, right? And steady state at the end, right? So what's that mean about the switch in this problem? So switch is open. All right. The switch opens at t equal to 0, then it goes through its transient, and then I get to I of infinity. So that's we say I of infinity, meaning t after a long time. All right. So after a long time, how am I going to simplify this circuit? Well, so I have the 2K, that's there no matter what. What do I do with the inductor that's in parallel with that 2K? Short it, because I'm talking about steady state. Now the current's still going this direction. I'll say IL of infinity is there. What do I do with that next branch with the 2K and the 12 volts? It's gone, right? Totally gone, right? Because the switch basically has been opened, right? And the only thing left is the 3K and this 6 volts. All right. Now, does the 2K matter? No, for the same reasons that we had before, the 2K doesn't matter to me. There's no current going down that branch. That circuit looks exactly like what we just did here. Right? If I look at it carefully, it's the same thing I did there. You can watch the video later if you don't follow me. Right? IL of infinity is equal to -6 over 3,000. All right, without me doing any work. All right, so now I got to get to the third step. The third step is to get the equivalent circuit. So in other words, I want to get this guy down to what is going to amount to this. I want to get him down to a picture where I've got a V open circuit, an R Thevenin, and then over here at the terminals is where my L is going to go. All right. So I want to get it down to a single series circuit like that. All right. So what I have to do is I got to say, well, what Thevenin equivalent am I making, right? So I got to figure out what I do to this circuit to make that happen. All right. Basically, and what time period am I considering when I do this? Between what and what? Yeah, between basically time t equal to 0 and infinity, right? During that time period. So do I leave the inductor in? Yeah, I'm leaving the inductor in. But what I'm doing is I got to simplify the circuit. Okay. So what I do is I look at it like this. So I drew these little circles here. Those circles to me are terminals, right? On the edge of the circuit. So basically it's like I replace this thing. I say I got 2K. And I remove the L. Okay. And do I need to include this branch with the 2K and the 12 volts? No, I don't, because during that time period, this whole time period, that switch is open, right? So I got the 3K and I got the 6 volts. Okay. Now, from my perspective, what I want to do is I want to find a Thevenin equivalent circuit looking into these terminals. So in other words, looking into those terminals, I can simplify that circuit down into an open circuit voltage and an R Thevenin. All right. Now this is a part that always kind of messes people up. Okay. So first part I want to do is the open circuit voltage. I want to find the open circuit voltage. What does that mean? Well, that means that if these terminals were just sitting here, I want to figure out what's the voltage at those terminals. So I'm going to call this here VOC. Okay. So what is VOC going to be? No, well, maybe it is. I'm not sure. Don't give me a number. How would I solve for it? How'd you get to 6? What is VOC in the circuit? It's the voltage across what? The voltage across the 2K resistor, right? So basically, again, how do I know it's the voltage across the 2K? If you can't tell, do a KVL around this loop, right? Do KVL around that loop. VOC is the voltage across the 2K resistor. Okay. So it looks to me like what I have here. Where's current flowing in this circuit, by the way? What loop is current flowing through? Just the outside, right? Going through the 3K and the 2K and back to the 6-volt source, right? So I'd say I got a voltage divider here. So VOC equals what? If it's a voltage divider. If you don't remember a voltage divider, it's really easy to do by saying, figure out the current in the circuit and then multiply by 2 kilo ohms, right? So, but if it is a voltage divider, what is it? You should know that. So it's going to be negative 6 volts times 2 kilo ohms divided by 2 kilo ohms plus 3 kilo ohms, like that. All right. If you don't know that, don't stress about it. Negative 6 divided by the sum of the resistances. Negative 6 divided by the sum of the resistances is the current. Times 2K is the voltage across there. Right. That's the way you would. There's no sense to. I mean, it's something we do so commonly, right? That it's good to remember it, but there's no reason to remember it. You could remember it as basically what's the total current times the resistance to get the voltage. Yes, sir.
Isn't negative 6 because the loop is going this way?
It's negative 6 because this is a negative 6-volt source, right? And you're right, because of the way the currents would be flowing, right? Like if I did this slowly, right, and I said, okay, if I just the way that you should have learned a voltage divider is like this. The formula for that would be, okay, the voltage across there would be R2 over R1 plus R2 times V. Pattern matching that to this, it's the negative 6. But if you didn't want to follow that pattern matching, you would say the current in this circuit is negative 6 divided by 2K plus 3K. Because of the fact that the voltage source would be pushing its current that way. Okay. All right. So I got what the open circuit voltage is. I also have to figure out the Thevenin equivalent resistance, right? So here's our circuit. What is a Thevenin equivalent resistance? Yeah, that's a fun question, isn't it? What is it?
The full resistance of the circuit.
Well, yeah, so it's confusing to people, right? The way I look at this is I say, okay, well, if I had a current source that was connected at those terminals, what resistance would that current flow through? Okay. In other words, if I hooked up a current source right here, we turn off the sources, because in this case, the sources don't have resistances to them or whatever, right? So I turn off the sources. That's the important thing, right? We turn off the sources. So turning off a voltage source means that I set it equal to 0. All right. And I say to myself, all right, that current that goes into those terminals, right? Where's it going to flow? It's going to flow and go around, right? So in other words, it's going to flow through a parallel combination of resistors. So the R Thevenin is basically the equivalent resistance that current's going to flow through, which in this case is going to be 3K in parallel with 2K, right? So the way to think of it is, how is that current going to flow into that circuit? Now, sometimes people look at this, and I see a lot of people, particularly, early on in the semester, they start saying, well, it's 3 in parallel with 2. All right. Or sorry, it's 3 in series with 2. It's not. You got to think of it in terms of, from the perspective of this terminal right here, which way would current flow into those terminals? It's going to flow into the parallel combination. So the equivalent resistance, right, would basically be the parallel combination of those two. You're not sure about that, someone can take some more time in recitation on Friday or something like that. But it's a concept that a lot of people struggle with, and you need to get comfortable with it, okay? Because we're going to use a lot for these types of problems. Questions about that? All right, if I get a number for that, I think it works out to like 1,800. I think. Should have worked that out for myself. It is no 1,200. All right. This works out to be 1,200 ohms. All right. Somebody can check me on that. I think that's right. What is right is 3K in parallel with 12K. So I sometimes I'll tell you, don't give me numbers because I don't know the numbers and I'm not as concerned about the numbers. What I'm more concerned about is you understand why it's 3 in parallel with 2. Okay. All right. So at this point, I've simplified this guy down into an equivalent circuit where I have my VOC. I have my R Thevenin. And I have my L. Okay. And I can put in what those numbers are. I should probably, what are they? I don't want to put in the numbers. All right. They're whatever they are. All right. So what I want to do is I want to figure out, I want to get to my step 4. My step 4 here. My steps. Step 4 was to write the differential equation. Okay. So how do I do that? How do I write the differential equation here? KVL. Okay. Let's do that. 0 equals, and again, I always start in this corner and I work around clockwise. So how do I write that out? In terms of what I've written right here, 0 equals what?
Negative VOC.
Negative VOC plus IL times RTH. All right, so I write that guy plus to minus. And I've written VL as plus to minus, so I would say plus VL. Okay, so VOC equals IL times RTH plus VL. What do we know about VL? There's an Ohm's law type of relationship, except it's ugly, right? VL equals what times what? L times. Anybody? Yep, DIL by dt. Yeah, good. All right, so now I got a differential equation, right? This is first order. IL times RTH plus L DIL by dt. Now, I said the other day, we want to get this into some form where I have a constant equal to a dx by dt plus tau times x. All right. I want to get it into that form. No, I did not say that. I said into that form. All right. So it looks like that. Okay. So in this case, X is what? I made this real general. X is always going to be the capacitor voltage or the inductor current, right? So in this case, what's my X? Like what variable over here is X?
That's the current.
It's the current. Yeah, it's the inductor current, I sub L. All right. So in other words, this guy here, what I want to do is I want to divide both sides by the resistance, right? That'll get it into this form, right? So I have VOC divided by RTH equals IL plus L over RTH times DIL by dt. Like that. Okay. So what's the time constant? Tau. L over R. So tau is L over RTH. Okay. So what we said is, that was really step 4 that I wrote there. So I guess I'll call this, since I had extra space, so step 4. Step 4 was differential equation. All right. My step 5 was to, if I go back to what my steps were, my definition of step 5 was to basically get the solution, solve the differential equation. All right. And I gave this guy a general form. I said, for step 5, basically I have IL of t is equal to my final value, IL of infinity, plus a e to the negative t over tau. All right. And we already said that VOC divided by RTH, IL of t plus L over RTH. That was our differential equation. Okay. And we defined tau to be L over RTH. Okay. I like working in symbols a lot more than I like working in numbers, because the numbers are different from every problem to the next, but the formula is not. All right. We get a lot more intuition from working with the symbols than we do with working with the numbers. Okay. All right. IL of infinity is something we already solved for. All right. We got that value a long time ago, and back in step 2, and that value worked out to be -6 over 3,000. Okay. What do I not know here? Skipping steps. A. Okay. How do I get that unknown? From my initial condition, right? Right. What I say is that I solved for IL of 0 minus. We said the inductor current always has to be continuous. So IL of 0 minus right before the switch moves and right after the switch moves is the same. Okay. So basically, I know what that number is. IL of 0 is known to me. IL of infinity was -6 over 3,000. All right. Plus a times e to the negative t over tau. So what's e to the negative t over tau? Well, if t is equal to 0, what's e to the 0? 1. So basically, I have that a here is equal to IL of 0 minus IL of infinity. Like that. And I got my answer. Now we can put numbers into all that stuff, and we should, we have to. But that's our basic process. Okay. Questions about what I did there? All right. So I'm going to get out of here for a second. And I want to go to the way I would enter this into the MATLAB system. Okay, so if I go to the MATLAB system here, okay. So what I have down at the bottom is the set of assessment questions. So it's finding the current IL of 0. That's the initial condition. That was step 1. Step 2 is to find IL of infinity, the final value. The value of the open circuit voltage of the equivalent circuit, the equivalent resistance, the value of tau, and the value of the current given the vector t. All right, so let's look at what I got here. So IL of 0, if I go back to what I wrote down, IL of 0 was, where is it? IL of 0 was this guy right here, 12 over 2,000 minus 6 over 3,000. So I'm going to put that here so I can get rid of those brackets. I can keep them too if I wanted to. I don't have to get rid of them. I'd get rid of them. I say 12 over 2,000 minus 6 over 3,000. Okay. Now I could enter in everything here if I wanted to, but I don't want to. What I can do is I can hit submit. And if I hit submit, what it should tell me is that I was right for the first question and wrong for everything else, which it did. All right. So it told me I was right for the first one. It told me I was wrong for everything else because I didn't put anything else in. All right. So if I keep going with that and I say, okay, well, IL of infinity was, that was -6 over 3,000. And I run that. Now it should tell me that I'm right for the first two. And I am. Okay. So that's the basic process that we kind of keep going through to enter these things. All right. And you can, my suggestion to you is to do them one at a time. Look at what the assessments are and do them one at a time. What's going to happen is you're going to try to do them all. It's just like writing code, right? You write 30 pages of code and it breaks and you don't know where it broke. So you just keep going step by step to see where your problems are. Okay. And again, even for what I did here, right, where I did 12 over 2000 minus 6 over 3000, you don't have to do it that way if you don't want to, right? I made MATLAB do the math. You could have your calculator do it if you wanted to, and you could put in whatever your calculator gave you, right? Your calculator, at least for the second one, would have given you negative 0.00, well, I don't know, negative 0.00 something, right? You could put that in there if you wanted to. Okay. All right. Questions about that? There will be many later, but probably not yet. Okay. All right. So we're almost out of time again. But that's fine. We got plenty of time together on Friday. Because Friday we've got regular class and recitation. So I'm going to pick up with my examples and we're going to keep going into examples more in the recitation. Okay. So if I keep going, do I have enough time to even start anything? I don't have enough time to start something, but I guess what I can do here is what's my next example? My next example is another one. All right. Except he's uglier, right? What's ugly about him? Well, all sorts of stuff, but yeah, he's a dependent source. So key thing here, again, we'll do it Friday, but when I got a dependent source, I got him to get a Thevenin equivalent here at some point. If I have a dependent source and I got to do a Thevenin equivalent, what's that mean? What would that mean? What's that? Well, I don't get rid of the independent source. I mean, I get rid of the independent sources. Normally, you turn off the independent sources when you try to find your Thevenin impedance. When I have these guys, though, what I have to do is I have to apply a test source, or what I have to do is I have to say, figure out the open circuit voltage and the short circuit current. I got to figure out them both, and then I got to solve, right? VOC divided by ISC is going to be the Thevenin equivalent resistance. So we're going to do that next. All right. So to give you a sense of where we're going, again, we got a test next Friday. I'm going to give you a practice test next week so you guys can think it through. Homework's due on Tuesday. Okay. So the homework covers a lot of 2111 type stuff. All right. The last two problems on there are going to be problems of this variety. Okay. So there's 4 problems that are just review of circuits 1, and then there's 2 that are basically first order circuits. Although if you pay attention to what we were doing here, this was mostly a review of 2111, most of what we did. We're gonna do a lot of that. All right, there's gonna be a lot of just going through what we did before in 2111. All right, and I'll stop there.